Hello and welcome. So in this tutorial we'll learn about OpenCL in the Copernicus context. So OpenCL is a GPU accelerated parallel programming language which is based on C, and it can give you much faster and parallel operations on the elements which are pixels in the COP context. And by parallel I mean that it will create a unique work item for each and every pixel and evaluate our code on all of them at the same time instead of iterating over the elements one by one. And since GPUs are great at processing large arrays of data, especially images, it can be very fast. And before we learn more about it, we must know the difference between the OpenCL and the VEX node, which are both available in the COP context to create filters for your images. So when you use VEX to process a large number of pixels in your image, since it is iterative and also it runs on the CPU, it can get slower. But since OpenCL accelerates on the GPU, it can easily handle a large amount of pixels and process them parallelly. And most of the image filters can be built using it. And here you see the diagram showing how VEX and OpenCL will process your images. So for VEX, VEX will iterate through each and every element one by one, as you can see. So it will do the work for the first pixel first, and then go to the second pixel and evaluate the code, and then again go through each of the pixel one by one. It can also apply multi-threading, using which it can distribute the work in multiple threads, but that's still limited by the number of logical processor or the number of threads which are supported by your CPU. It can also optimize it using SIMD techniques like SSE or AVX if your CPU supports it, but that still can only hold a limited amount of element to process at the same time. But for OpenCL, every element is processed at the same time, and since it runs on the GPU, it can be really fast. OpenCL also has many basic variable types which you can use. For example, int will obviously store an integer, and these int2, int3 are just multi-component or multi-dimensional versions of it, so that you can store multiple integer values in it. For example, if you want to store a pixel coordinate, then you will store it in the int2, and floats store floating point numbers, and again these are just float 2, float 3, these are the multi-component version of it. And float values can be very useful. For example, you can use them to store pixel values. For example, if you have a mono image, and then you can store the pixel values in a float value variable type. And if you have a UV image, then you can store it in float 2. If you have a RGB, then you can store it in the float 3. And if you have a RGBA, then you can store it in the float 4. And there are also matrix variable types which you can use. It can be similar to the float types. For example, mat2 can be similar to float 4, but they are used in a lot of functions, and they are more specific. And OpenCL also gives you the feature to make custom variable types or objects using struct. You can use them if you want, but I won't talk about that in this video. Maybe I would in the next part. And before we head to Houdini, we should first learn about the windows and the spaces, because they are used a lot in the OpenCL and also other contexts of Copernicus. So in Copernicus, data and display windows are rectangular areas which are defined for the image, and data window determines the area in our image for which the pixel data is available in the memory or the buffer. And buffer is the data about the pixel in memory for use, and the display window determines the area which is visible in the viewport. And both of these windows can be bigger and smaller than the other one. For example, as you can see here, where the display window is 512 times 512 pixel long, but the data window is only 256 times 256 pixels long. So it is smaller than the display window. So it is the only part which is available for you to see. And the data window can also be larger than the display window. For example, the display, even if the display window is 512 times 512 pixels, the data window can be bigger than that. And for most of the normal images, for example, the ones which are stored in the JPEG or the PNG files, they mostly have the same data window and the display window size. But for EXR file types, it can be different. And in Copernicus, there are also many coordinate spaces which you can use. The buffer space is the raw pixel data layout in memory, and it is tied to the data window, obviously, because in memory the data is only available for the data window, as I said before. And the 0 on X and 0 on Y coordinate in the buffer space is the bottom left pixel coordinate in the data window. For example, if you have this 0 on X and 0 on Y coordinate, then even if the display window is bigger, the pixel would be over here, and that would go through as many pixels as we have, and the other coordinates will be going through all the other pixels which we have in the data window. And there is also the pixel space coordinate, which is similar to the buffer space, but that is tied to the display window. So the 0 on X and 0 on Y coordinate in the pixel space is the bottom left pixel coordinate in the display window. For example, when the data window is smaller, still the pixel space coordinate will be over here in the bottom left of the display window. And there are also floating point spaces, and the buffer space and pixel space coordinates are represented as an integer 2. The texture space goes from 0 to 1 in the X and Y coordinates, and it is tied to the data window. For example, 0 on X and 0 on Y will represent the bottom left coordinate of the pixel. And the image space goes from -1 to 1 in X and Y coordinates. And for the image space, the 0 on X and 0 on Y coordinate is the center of the image, and this space is tied to the display window. For example, if we have 0 on X and 0 on Y coordinate, then it will represent the pixel in the center over here. Yeah, and it will be tied to the display window. And there are also some things which you should note. The first one is that the GPUs have a hard memory limit, since it doesn't have anything like virtual memory or MMU to stop you from reaching the memory limit. So you should always optimize the amount of memory used. And since OpenCL is parallel, there can be some cases in which every element is trying to change something at the same time. For example, if there is a global variable and every element is trying to change it, then that can cause a race condition which won't make your Houdini crash, but it can give you unexpected results and you should avoid it. And now we'll head to Houdini and learn more. But before that, if you haven't subscribed my channel yet, please subscribe it, because that will help me a lot. So now we'll jump to Houdini. So over here we can drop down a COP network and jump aside and drop down a OpenCL load, and we will clear all the default code. And also we'll go to the composite view. If you don't have this window open, then you can open it by clicking on this plus icon, then new pen tab type, and then viewers and composite view. Click on it and it will open it for you. And I have also changed the background color by pressing D and going to the background and changing the background color. To make this OpenCL node work at first, we should first go to the signature tab and clear all the inputs and the outputs which our earlier default code binded. And now we'll look at binding. So to have access to an external data, for example, an image layer or a parameter, you have to bind it in OpenCL. And to do that, the basic syntax for it is you first write this hashtag and then you say bind, and then you write the data type, and then you have to write the data name, and then you have to write the tag. And this is the basic syntax for it, and we don't want this to be compiled or be seen by the compiler, so we can command it, and you can do that by writing 2 backslashes before it like this. So this will be the basic syntax which we will follow. So to bind a simple image layer, the data type for that is layer, and you do it by writing bind, and then you have to say layer, and that will bind a image layer input, and then you can give it a name which we will later use to access it. So it can be test layer, and then we can just run this. And to create the input for this, you have to click on this create inputs and spare parameters. So you have to click it, and now you have this input binded. And just like this, you can also bind parameters on the node using the parm data type. You write it like this. So you will first say bind and then parm, and let's call it test parm. And now if we hit this create inputs and spare parameters again, we'll get this test parm parameter. And you can also use flags to change the options or information about this data which you have binded. For example, you can use data flags to tell what kind of data that input or parameter gives you. For example, for this layer, we can say float2 here, and this parameter we can make it a integer. And if we clear these previous bindings by going to signature tab and clearing, and then also in the binding, we can delete the parameter bindings we made. So just right click on this 3 lines and click on this delete selected instance. We'll learn more about these windows in a minute. And now if we delete this parameter by right clicking and going to more and delete spare parameter and delete. Now we can create the inputs and spare parameters again. And now as you can see, this input, as you can see, wants a UV, and this test parameter now wants an int value, because we stated that using these data flags. As you can see, this is the flag part of our binding. And then you also have access flags, which determines that if our data which we have binded is, for example, non-readable or writable or readable or maybe optional. And the most used ones are the no read and write and the optional flag. For example, if you want to make a output layer for this OpenCL node, you have to make that layer which you have binded a writable layer. So we can do it below it. For example, we can bind in another layer and call it out, and that can also be a float2. For example, float3, which will be RGB, and we can also give it the write flag like this. And now if we create the spare parameters and the inputs for this, as you can see, we have this out as an output too, because it is writable. And if you don't want a input for that also, then you can also provide it this no read flag. This will make it non-readable. and that would mean that we can't read it from our inputs. So we can also provide it that, and we can delete the binding for the previous one in the signature tab. So delete selected instances and clear the outputs, and then we can create the inputs again. And now, since we have provided this no read flag, it is only available as an output. You can also make a readable data which you have binded an optional type of data, so that it isn't necessary to give your node that information. And to do that, for example, we can make this test layer input an optional, so that our node doesn't complain like this that the test layer is missing. So we can mark this as an optional input by using the opt flag, and then we have to clear this, the previously generated one, and then create the inputs. And currently the node has started to complain because we don't have a kernel, which we have, because we fixed the issue with the input that we didn't provide. So let's also create a kernel to fix this issue. So over here we can write at, then in capital letters you have to write kernel, and this is the kernel. Now the node will stop complaining and it will give us this default image. So the kernel is the main part of your OpenCL code, and the code which you will put inside it will run for each and every element or the pixel in our image. And right now, since we have a output layer binded, as you can see it, this one, which is a no read and write layer, so that we only have a output for this. We can also write in that, and to write in it, we first have to access that data using the access syntax. So you first have to write at, and then the name of the data which you have provided over here, the name of the image layer, the name of that is out, and then you can use the internal functions which this image layer type provide, and one of them are the set function. So you have to put a dot, and then it will give you the access to the internal functions, and then you can use the set function. For example, you can set that output image to a float 3 value, because it expects a float 3 value. So we can make a variable for that. So we can write float 3 and then the name of that variable, and then we can assign it to some value, for example 0 or 1 and 1 and 1, or 1 0 0. That will give us red color, and we can then set the pixel which our kernel is giving us to that value. So we can write var over here, and then if you evaluate it, now the color is red. And you can also change it. For example, you can make it green by making this one 1, and now it is green. And just like that, you can also make it blue by changing this, the third component, the blue component, to 1, and now it is blue. And as you can see, it is very hard to change it directly in the code, so we can use the parameters which we have binded over here, but currently it is int and not a float type, so we have to make it a float. So let's write float over here, and we can also make it optional. And when a data is optional, you can also provide a default value for it, and to do that you have to use the val flag. So I will write it over here, val flag for defaults. So we can write val, and then we have to provide the value which we want to use as the default value. We have to say equal, and then let's make the default 1.0. And now we can delete the previous parameter which we have binded by going to the bindings tab and deleting the previously binded parameter, and then we can delete it from here too. and then we can create the new one. And just like how we access the output layer over here using this add syntax, we can also do that for the parameters. So we can write add and then the test parm, the name of the parameter, the data. And now if you change this, you will adjust the amount of blue color it gets. And now you can also create two more parameters for these two values, but that would be a waste of time. And now we can learn that how we can use our input layers to access the data from it. And first thing I want to tell you, since with these access flags, it can our binding lines can get very big, so there are also some shortcut characters for it. For example, for no read, you can use this exclamation mark instead, and for the write flag, you can also use this and mark, and for optional, you can use the question mark character. So for example, we can replace these flags with those shortcut characters. So we can write question mark instead of this opt flag. And for no read and write, you can also combine these flags. So instead of writing that lengthy words, we can use the exclamation mark for no read and the end mark for write instead. And also for this one, we can use this question mark to replace the opt flag, and that will still work. So if we try to clear all the our outputs and inputs and recreate them, we still have them working. So the out layer which we abandoned is still the output because it is still writable, and it is not creating an input port for this because we have this no read flag. And it can be hard to remember, but when you use it a lot, you will remember it. So we can now learn that how we can access the data from the input layers. The one which we have right now is a UV, so we can change it to a float 3 to be RGB and clear that previous input and create it again, and let's rename it to in. And now we have this in input, and as a test image we can use default one which the file node gives us. So you can drop down a file node and this will give you this default butterfly image. There's also another default image which you can use, which is called mandrill. Yeah, this one, or you can just use the default one, the butterfly one. And currently it is RGBA or float 4, so we have to turn it to float 3 or RGB, and then we can connect it to our input. And currently nothing changes because in kernel we are not using it. And as I said before, inside the kernel you write the code which runs for each and every pixel, and you have the information about that specific pixel which the kernel is currently running for. So we can access that value for the current pixel which our kernel is running for, and then we can set that for our output. So for example, we can keep this float 3 and we can just set it to the value for the current pixel in our input layer. And for that, again, you have to use the access syntax, and then you have to provide the name of that data or the image there, and then you will be able to access that current pixel value, and then it will be stored in this float 3 variable, and then we'll set our output to that, and now it will work like a pass-through. As you can see, the same image goes through it. And instead of using this variable over here, we can save some memory and directly do it in this set function. So we can over here say add in, and that would also work. but this is more specific. So we'll keep, and since we have it stored in a variable, we can access the actual power of OpenCL by modifying it. So we can take this var and, for example, set it to var times some value. Let's use our test parameter which we have binded over here. Use test var using this access syntax at and then the data name, which is a parameter data. And now it will work as a multiplier. So if we have it set on 0, then 0 multiplied by any value gives 0, obviously. And if we set it on 1, then that gives the same value as we had in the variable. And anything in between will reduce the values. And you can also shorten this syntax instead of saying var equals var times at test per pam. Instead, you can write var times equals test pam, and that will be the same as you can see. And for example, we can also invert our values to invert our image. So we can keep that multiply part in, and before it we can invert our pixel values. And to do that, if you know that the minimum value for your pixel will be 0 and maximum will be some value, then you can use that maximum value which you know and subtract your current pixel value from it, and that will invert your value. And you can take a look at your if your minimum value is 0 and the maximum value by looking at the histogram. So if we set the display flag on the original pixel, over here on the composite view you have this third viewing option, which is histogram. And a histogram shows us that for a specific value, how many pixels are using that value. For example, you can see that for the value of 0.3, very low amount of pixels are using it. But for the value between 0 and 0.1, there are a lot of pixels which are using it. And for the complete black 0 value, there are a lot of pixels using it because that's the background color. So we know that the minimum value is 0 because, as you can see, no values are getting in the other side, and the maximum is 1. So to invert this picture in our OpenCL node, we can do var and then var equals var 1.0f minus var, and then it will just invert it, as you can see. And this f which I put over here, if I want put it over here, then it will think that this 1.0 without that f is a double or a 64-bit float value. And to store it in a float which is a 32-bit value, it will have to make conversions, which can also be slow. So we can write it over here as a float, and now it will know that it is a float, and it won't do any conversion. So as you can see, our image is now inverted, and the background, which was completely dark, is now white, and the other parts are also inverted. You can also use other pictures, for example, and that will also get inverted. So this is the original, and this is the inverted one, and then you can also multiply the value. So now we can take a look at all of the tabs which we have over here on this OpenCL node. In the options tab, you have a lot of options to customize how your OpenCL node works. For example, you can set the run over method, which by default is the first writable layer, and there are also other options which are not needed for us because we are only going to use our OpenCL node for images. And then there is the name of the kernels. There is the name of the main kernel and the writeback kernel, which we didn't talk about yet, but we'll learn about it in a minute. And this is not the name of the kernel which you write over here. It is the name of the kernel in the generated code for it, which we will take a look at in a second. You can also provide compiler options and flags for the compiler, and you can also specify layer tile size, and you can use it to run your kernel on a block of pixels. For example, if you set it to the layer tile size to 2 by 2, if you zoom it in, then it will process 2 times 2 pixels or 4 pixels in a group, and currently it is only setting the value for the first buffer element of that tile. So as you can see, we are taking these 1, 2 and 3 and 4 pixels in account, and we are only modifying the first pixel. I don't know the correct use case of this, but I think you can use it to run your OpenCL node on groups of pixels. So we can set that back to the default. And you can also specify the iteration count, which can be used to iterate over your kernel code multiple times. For example, if you specify 2 over here, then it will run the kernel 2 times. And you can also include the iteration count so that it is available as a value to use in the kernel, which you can access by doing add and then iteration. I think that's it. So now we can visualize that iteration value by setting that as our pixel value. And to do that, we have to convert the integer iteration value to a float, and then we can set that to this float 3 variable. And to do that, to convert a integer to float, or to convert any type to another type if it is making sense, then you have to first open a bracket and then specify the type which you want to convert it to. So right now we want to convert it to float, and then the thing which you want to convert, so it is iteration, and then it will be set to a variable. And then we can comment this line out because this is doing the inversion. You can keep the multiplication part, because if it is set on 1, then it won't affect anything. And now we can leave it. And to check the pixel value, what you can do is you can right click and then click on this inspect button, and this is only available if you are in the composite view window. And now you can inspect the pixel coordinates and also the pixel values. So for example, if we change the iteration count, it will be outputted over here. And you will notice that if our iteration count is 1, then this iteration which we get from this include iteration option will be 0. As you can see, these 3 values over here, they are the pixel value, because currently our layer is RGB, that's why we have 3 values. And it is 0 because obviously when your iteration count is 1, the kernel is only going to run once, and that's why it is the iteration count is 0 for this. When you increase this, for example, to 2, it will become 1, and then if you set it to 3, then it will become 2. And if you want to match this to this, then you can just add 1 to this. Add 1, and now it is also 3. Now we don't need this one anymore, obviously, so we can remove this. We can set this back to the default, and also this include iteration. And now we'll learn about the writeback kernel, which is the second type of the kernel. So you have to turn it on, and then there will be some errors because we obviously didn't define that over here. So what you have to do is just write at, and then in capital letters write writeback, and then the brackets, and this is your writeback kernel inside it. And now no errors will appear. And this writeback kernel will run after the main kernel has finished its work. So for example, we can check that if we make our out layer readable, our output layer readable, then obviously it would also want to create a input for this. So we'll create that input, and we can just plug in the same image. And if you don't want to plug this wire in, then you can obviously make this optional by providing the optional flags shortcut, which is question mark. And now even if we recreate this, so delete the one which we already have, and then recreate that. And if you even cut that wire, because it is optional, then it won't worry about that. And now when the kernel has done the job, we can take that output layer which has the values set. So over here for all of the pixel we set the values using this main kernel, and then we can do things with it in the writeback kernel. So for example, we can say at out dot set, and we'll set it to at out times, so the current value of out which has been set in the main kernel, and then we'll multiply that by, for example, 0.1 f. And now we can run this, and as you can see, the pixel values are named now. And what we can also do with it is that we can make a feedback loop with it using the iteration count which we have over here, which we learned about, and this writeback kernel. And to do that, what we will basically do is that we will make this our input writable, and then after the main kernel has run, we'll write the output value to that input. And then when we increase the iteration count, the kernel will run again in the next iteration, and it will have that value as a feedback. And using that, we will create a feedback loop. So to do that, first we have to make this a writable layer. Let's do that. We'll use this AND character which is for the write flag, and then we'll create the output for that, and we don't need to plug anything to that. And now what we have to do is we have to say at in dot set, and we'll set it to the current output value. And now if we let's just remove this inversion part and only keep the multiplier. So if we increase the iteration, as you can see, it slowly fades out as a feedback loop. You can also set it to $F to make this time based. So when you run your frame, it will slowly fade out. And you can obviously do more things with it. For example, you can do anything with it if you want. And there are many more use cases of this writeback kernel, but right now we don't need it, so we will remove it. And again, we'll make this input a read only, and will make our output a non-readable one. And we can remove this optional flag because obviously a non-readable input doesn't need any input to it, so it obviously doesn't need to be optional. And then we'll remove these default ones and recreate them. And then we'll go over here and turn off use writeback kernel because we don't need that. And include time option will give you a add time value to use, which will change with your frame number. So on the 24th frame, I think 25th, it will become that add time value will be 1, and just like that it will increase in seconds. And to access that, for example, we can try it by multiplying it with our pixel values. And to access it, you have to say add and then time. And now at the frame 1, obviously the time in seconds is 0, so we are getting no output at all. If we play it, as you can see, it slowly reveals out and gets brighter and brighter. And we don't need it now, so we can reset that to add this bar and remove this include time. And these all of these three parameters are just to do things with the time. And this one, use import for prequel code or include. We'll learn about it when we will talk about preprocessor, so you don't need to worry about it right now. We'll learn about it in a minute. And this timing messages will give you the information about how much time it took to compile the generated code, and then how much time it took to cook it with this input. So if you immediately click on it, as you can see, compile plus mine took 0.31 millisecond and cook took 0.74 millisecond. And you can obviously see the both of them in the performance monitor if you enable it, or you can just middle click and check this last cook time. And now we'll learn about this signature tab, and we obviously used it a lot to reset our inputs and outputs, but what it is also used for is to set the information or the signature about that layer. So for example, we obviously have this input layer binded, which is a float 3, and when we click on this create inputs and spare parameters, it automatically creates this input matches the flags which we set over here. So as you can see, we set the optional and the float 3 flag, which makes it a RGB layer, and it is optional. And one thing you should have noticed in the options tab about our output layer is that we have set our run over to the first writable layer, as you can see. And this means that the layer which is our first writable layer, which is our output layer, it will run over the output layer's pixel. But if we haven't set it to this 512 times 512 resolution, how does this know that it is this resolution? And the answer is in the signature tab too. So as you can see, we have this output binding for our output layer, and in the metadata you have it set on the first input, and that means that it will take the all kind of image data from the first input which we have, and that's where it is taking this resolution and the other information from. And you can obviously change it to, for example, input name, and then if you have multiple inputs binded over here, then it will take the metadata from that input. And you can also set the precision. So if you want your output to be 16-bit or 32-bit, or you can also obviously set it on the input precision. And the layer type is also input, and it will take all the other kind of information from this first input. For example, the layer border type or the color and anything like that. And this bindings tab is obviously for the parameter binding, as you can see. For example, we have binded this test param and the type is float. You can obviously customize that, but it is currently taken automatically by because we click on this create inputs and spare parameter button, and the precision is 32-bit, and our value is same as this, and our you can also set the time scale. And the generated code tab, if you click on this display code button, this is the actual code which gets generated for this which we write in our on this kernel code, and all those functions and all the other things are defined over here. For example, you will see all of these, for example, this fit01 lerp and all of these functions which are defined locally for our main code, which you can use obviously in this. And as I said before, in this option tab, we have this kernel name and the writeback kernel name, which is set on generic kernel, but we are not using that over here. That's actually used in this generated code. So if you see, go to the end of this. So over here, you will see that we have a kernel which is generated and the name is generic kernel. So this just shows the main code which is built for your for what you write over here. And you can obviously also take a look at all the locally defined functions which we have over here, and use them if you want. And what a function does is that it takes some parameters if it wants, and then does something with it and returns some value if it wants. And we can obviously define our own functions inside our own code. And you obviously don't write it inside this add kernel because you don't want to define it for every element. You do it outside the kernel because it is supposed to be defined globally. And anything which is supposed to be done globally and not for per element, it won't be inside the kernel, it will be outside the kernel. And now we'll learn about functions and coordinates and preprocessor flags and all the other things in the next part.